So in this video, we're going to train a neural network to classify newswires from the Reuters news agency. Reuters publishes these newswires, which are things like this here. It's like a little headline or a little mini story, a little mini news blurb. So for example, here's one: Boeing plans 737 MAX production restart by May. And here's another newswire that says, Taiwan reports 19 new coronavirus cases. And let's see, US government agrees stimulus package in response to coronavirus pandemic. So we're going to classify a data set consisting of these newswires. The neural network architecture we're going to use looks like this. We have two hidden layers. We have an input layer. Each newswire is going to be represented by a feature vector with 10,000 features. So the input layer is going to have 10,000 inputs. The first hidden layer is going to have 64 nodes, and each node will use the ReLU activation function. The second hidden layer will also use 64 nodes, each using the ReLU activation function. And in this classification problem, we're going to have 46 classes. So it's a multi-class classification problem with 46 classes. The final layer, the output layer of our neural network, is going to have 46 nodes. And the outputs, each of these 46 outputs, that's going to give us a vector in R46. That vector is going to be plugged into the softmax function. That's going to give us a probability vector, which tells us the probability that the training example we're looking at belongs to each of the 46 classes. Let's count up how many parameters we have in our neural network. So how many parameters does this particular node have? This node is a tiny little individual computational unit. And what it does, the computation it performs, is it takes this vector as input. That's a vector of 10,000 numbers. It computes a dot product, and then it adds a bias term, and the resulting scalar is fed into that. It fed into the ReLU activation function. So this node has a vector with a vector of 10,000 weights, and it has a bias term. So that's 10,001 parameters that belong to this node alone. And so for this first hidden layer, the number of parameters is 10,001 times 64, because we have 64 nodes in this layer. Now, let's look at this node. How many parameters are there that belong to this node? What this node does is it takes the outputs from the previous layer, that's a vector in R64. It computes a dot product against that vector, and then it adds a bias term, and the resulting number gets plugged into the ReLU activation function. So this node has a vector in R64 that it uses to compute its dot product. It also has a bias term, so that's 65 parameters that belong to this node. So the number of parameters in this layer is 65 times 64, because this layer has 64 nodes. And now, how many parameters does this node have? Well, this node takes the output from the previous layer, that's a vector in R64. It computes a dot product, adds a bias, plugs into the ReLU function. So that means that this node has 65 parameters. And the number of nodes in this final layer is 46. So this is the number of parameters in the final layer of our neural network. Now we're going to create our neural network and train it using Tensorflow. So here we're importing a bunch of useful libraries, including Tensorflow. In this line of code here, we're reading in the Reuters dataset. The Reuters dataset is one of the datasets it's built into TensorFlow. Here's a list of the 46 categories we have. for these newswires. So some of the newswires are on the topic of cocoa, some are about grain, some will be classified as about earnings, some are on the topic of acquisitions, wheat, copper, and so on. 46 categories. Okay, let's just look at some of our newswires. Here is a little snippet of code that, well, let's look at the data that we've read in so far. What do we have so far? We've got something called train data, which is a NumPy array, and it's just a list, it's an array with 8,982 elements. And let's look at the first element of train data. So it's the first element, the first example in our training data set is a list of integers. Let's do, let's print out train data of 0, and then let's call this xi. So then xi is just a list, and the length of this list is 87. And let's print out the first 10 entries in this list. So it's a list of integers. Each of the, just like when we were working with IMDb movie reviews, each of these integers corresponds to a word in our dictionary. And we have 10,000 words in our dictionary. When we read in the data, we used this argument here, which said that out of all the words that appear in all of the Reuters newswires in our data set, we are only going to keep the 10,000 most common words, the 10,000 most popular words, and those are going to comprise the dictionary that we're working with. And so this training example here is just a list of integers. Each integer corresponds to a word. Now let's decode this newswire so that we can actually read it. And here is a little snippet of code that decodes a particular newswire. So if I run this little snippet of code, then we get the English version of our newswire. So this list of integers has been translated into a list of English words. So said as a result of its December acquisition, ... So this is something we can read now. Here's another one. Let's look at this one. Here's another example of a newswire in our data set. A large Dutch animal feed will begin formal legal proceedings early next month. And let's look at what's the label for this data set. So let's look at, for this training example, what's the label? Let's look at train labels of IDX. The label is 1, and let's look at categories of 1. So the label for this newswire is grain, and that seems to make sense because it's talking about animal feed, and here's the word grain. So this particular newswire is on the topic of grain. Okay, so this is the data that we have. And now what we need to do before we can feed our data into a neural network, we need each of these newswires to be stored as a vector. And we're going to use the same vectorization strategy that we used with the IMDb data set. So each of these newswires is going to be represented as a vector with 10,000 components. And the ith component is going to be equal to 1 if the ith word in our dictionary appears in the newswire. Otherwise, the ith component is going to be equal to 0. And so that's how we're going to construct a feature vector in R10,000 that describes a particular newswire. Here's a snippet of code that will vectorize our data. It will construct a feature vector in R10,000 for each of the training examples in our data set. So let's run the snippet of code and let's see what we have. We have something called xtrain, which is a NumPy array, and it has 8,982 rows, 10,000 columns. So each row of this array is a feature vector. Each feature vector has 10,000 numbers, 10,000 features. So let's look at the first row. And the first row is just a list of 10,000 numbers. And let's print out the first 20 components of this feature vector. So they're all zeros and ones. So this component is a 1. That tells us that the item in our dictionary with index 1 appears in this newswire. And here, this entry is a 1 that tells us that the item in our dictionary with index 2 appears in our newswire. So that's how we represent newswires as feature vectors. So now that we've constructed our feature vectors, next we need to do one-hot encoding on the labels. Currently, the labels are just integers between 0 and 45. So let's look at the first 10 labels in our training data set. They're all integers from between 0 and 45. That's because we have 46 classes. And the maximum label is 45. That makes sense. Okay, we need to do one-hot encoding on our labels. So TensorFlow gives us this function, which is called toCategorical, that just does the one-hot encoding for us. So let's run this section of code, and now ytrain is an array that contains one-hot encoded label vectors and for all the training examples in our training data set. And ytest is an array that contains one-hot encoded label vectors for all the examples in our test data set. And let's look at ytrain of 0. It's just, there it is. It's just a one-hot encoded vector. We have a 1 here. That means that the class, that means that this example belongs to class 3. And if we look at training, if we look at train labels of 0, it's a 3. That's consistent. It belongs to category 3, the third category. And how do you represent 3 when we're doing one-hot encoding? You represent category 3 like this. There's a 1 in position 3. Keep in mind that when we're training our model using stochastic gradient descent is not going to be allowed to look at the validation set. It's only going to be allowed to look at the training data. So measuring the performance of our neural network on the training data alone would be a bad idea, because that would be like cheating. The stochastic gradient descent was looking at the training data when it was tuning the parameters of our neural network. That's like cheating. We have to look at how our model performs on the validation data set to see if our model is really doing a good job or not. So next we have the section of code where we specify the architecture of our neural network. So as we discussed, we're going to have a hidden layer that has 64 nodes. Each node uses the ReLU activation function. Then we're going to have another hidden layer, which has 64 nodes. And then each of those nodes uses the ReLU activation function. Then we have a final output layer with 46 nodes. Those 46 outputs, that's a vector in R46. That vector will be plugged into the softmax function. That will give us a probability vector. And in this line of code, we compile our model. When we compile our model, we are telling TensorFlow which optimization algorithm to use. We're going to use this algorithm called RMS prop, which is similar in spirit to stochastic gradient descent. We're also telling TensorFlow which loss function to use. Because we're doing multi-class classification, the loss function we're going to use is the categorical cross-entropy loss function. And we also tell TensorFlow which metrics to keep track of during training. So it's going to keep track of accuracy, classification accuracy. When we train our model, we're going to use 20 epochs. And this is the line of code where we actually train our model. And we're telling TensorFlow to use a batch size of 512. So what that means is that at each step of stochastic gradient descent, we are going to compute our gradient based on 512 training examples, which are selected at random. Remember, in stochastic gradient descent, we don't compute the full gradient vector that uses all of the training data. We only select a subset of the training examples, in this case 512, and we compute a gradient based on that subset. And we're telling TensorFlow here to keep track of how we're doing on the validation data. So as the iteration performs. So stochastic gradient descent is not allowed to look at the validation data. And that would be cheating. But it's still okay for us to monitor our progress on the validation data as the SGD, as the optimization algorithm progresses. And then, so let's run this section of code to train our model. So we're doing 20 epochs, and we can see our loss function is being reduced. As our neural network training progresses, TensorFlow keeps track of the cost function value and the classification accuracy at each epoch of stochastic gradient descent. And that information is stored in this variable history. So this variable training loss here, that's a list of the training loss at each epoch of stochastic gradient descent. And this is the cost function value computed using the training data. Here, what we have is a list of cost function values at each epoch of stochastic gradient descent. But these cost function values are computed using the validation data rather than the training data. And here we have a list that tells us the classification accuracy at each epoch of stochastic gradient descent. This is classification accuracy computed on the training data set. And this is a list that tells us the classification accuracy at each epoch, but now the classification accuracy has been computed using the validation data. So let's plot the training loss and the validation loss at each epoch. And here we go. Here's the plot we get. So we can see that the training loss continues to go down when throughout the entire stochastic gradient descent process. But after about 3 epochs, or actually after about 7 or 8 epochs, we stop making progress on the validation data set. The validation loss actually starts to get worse after about 9 epochs. So this is overfitting. This is what it means to overfit. We continue to improve on the training data set, but the performance of our neural network on the validation data set is getting worse. So we're overfitting. Let's also plot the classification accuracy on both the training data set and the validation data set. So here's a plot of the classification accuracy. You can see that the classification accuracy continues to improve when we measure it on the training data set, but it plateaus after about 5 iterations, maybe. After 5 or 10 iterations, the classification accuracy is no longer improving on the validation data set. This is, again, a sign that overfitting is happening. At least there's no further progress on the validation data set. So based on these plots, it looks like maybe we should stop after 9 epochs. The simplest way to avoid overfitting is early stopping. We just stop the stochastic gradient descent iteration after a suitable number of epochs. In this case, it looks like 9 epochs is pretty good. So we're going to change this to 9. And then let's recreate our model. And then now we're training our model again, but this time we're using only 9 epochs. And there's a plot of our training loss and our validation loss. There's a plot of our training accuracy and validation accuracy. Now, finally, let's test how we do on the test data, which we have not yet touched. We haven't looked at the test data. This model.evaluate function what it does is it looks at the test data and it sees how our model performs on the test data. So our accuracy on the test data set is about 79%. So for a classification problem with 46 classes, getting about 80% accuracy is not bad. If we had randomly guessed, then our classification accuracy would have been much lower than 80%. For this data set, I believe the most popular class occurs about 20% of the time. So if we simply guess the most popular class every time, our classification accuracy would be like 20%. So with our neural network, we did much better. We got 80% accuracy. Now, as an experiment, let's look at what would have happened if our second hidden layer, instead of having 64 units, had only 4 hidden units, had only 4 nodes. What would have happened then? Let's retrain our model using that different architecture and see what happens. So now we're training our model. And a rule of thumb is that if you're doing multi-class classification with k classes, then you probably shouldn't have an intermediate layer which has fewer than k nodes. And let's observe that. If we compute our accuracy on the test set now, then our accuracy turns out to be 67%. So it dropped from 79% down to 67%. This example has been based on chapter 3 of the book Deep Learning with Python by Francois Chollet. It's an excellent book that I highly recommend. Here are a couple extra experiments you could try out with this example. You could try changing the number of nodes in each of the layers. So instead of 64 nodes, you could try 32 or 128 and see how that affects your classification accuracy. You could also, instead of using 2 hidden layers like we did, you could try using a single hidden layer or 3 hidden layers. And so what are some takeaways from this example? So here are some important things to observe. If you're doing multi-class classification with k classes, then your network should end with a dense layer with k outputs, a dense layer with k nodes. And that's because the output of each of those nodes, those k outputs are going to give you a vector in Rk. And that vector is going to get fed into the softmax function. And the softmax function, of course, is useful because it converts a vector into a probability vector. And that probability vector tells us the probability that the training example we're looking at belongs to each of the K classes. So the final dense layer in your neural network should use the softmax activation function. And then the loss function that you should use is the categorical cross entropy loss function, because in machine learning, that's how we compare probability vectors. We use cross entropy.